In an earlier lecture, we introduced Faraday's law, which tells us that a curly E field around a closed path is produced by a time-changing magnetic flux through a surface bounded by the closed path. Now, the left-hand side of Faraday's law, the integral of the scalar product of vector E with tiny displacements dl, looks familiar to us. We know that this expression has the units of volts, as does the right-hand side of Faraday's law. And the physical meaning of the integral is that the magnitude of the integral represents an EMF, and the magnitude of the flux time derivative as well represents an EMF. Now we know an EMF can serve as an energy source in a circuit. Now, in order to have a circuit with flowing current, we need a conductor. So let's imagine that we have a wire loop that follows the closed path around the shaded area. Faraday's law tells us that there would be an EMF around the circuit. So we would expect a conventional current, capital I, to flow in the wire loop in the direction of the curly electric field. We call this an induced current because the time-changing magnetic flux is said to induce the current in the loop. If we know the resistance, capital R, of the wire loop, then we can find I. It's just the EMF divided by the resistance R, just as we would expect for a single loop circuit with an EMF energy source and a single resistor. Now the power in the circuit, in this case the rate at which energy is being dissipated in the circuit, is given by the product of I times the EMF, which we can rewrite by replacing I as shown. Now let's recall that for any EMF, there is some non-electrical source for that energy. That's true here. The source of energy that's being dissipated in the wire loop comes from the gravitational potential energy of the magnet. As the magnet falls, gravitational potential energy decreases, the energy dissipated in the circuit increases, and all this happens in a way that satisfies conservation of energy. Energy is being converted from one form to another, but no energy is being created or destroyed. Now let's point out something else. We know the magnet is a source of magnetic field. Let's call that field vector B sub m for the magnet. Now since the wire loop is present and has an induced current I in the loop, the current loop is also a source of magnetic field. Let's discuss how the direction of that second magnetic field is related to Faraday's law. This is described by something known as Lenz's law, which states that the magnetic field from the induced current opposes the change in flux. Let's see how that works out here. As we discussed before, in this particular situation, as the magnet falls, the magnet's B field, vector B sub m, is increasing downward, which means the flux is changing by increasing downward. Lenz's law says that any currents induced by this changing flux will produce a second magnetic field that tries to oppose this change in flux. That means we'd expect the second magnetic field, the one due to the current loop, to be pointed up to try to offset the delta vector B sub m. We know that in order for the loop to produce that kind of vector B loop, the current must be counterclockwise, and that means the curly E field is also counterclockwise. That's Lenz's law. It's really just another way to relate the direction of the curly E field to the changing flux through the surface bounded by the closed path on which we have a conducting loop here. Now let me emphasize, Faraday's law does not mean you always get induced currents. You need a conductor to have currents. No conducting loop, no current. However, Faraday's law says you will always have a curly E field if you have time-changing magnetic fluxes, magnetic fields. So do keep this right-hand rule in mind as well when you are trying to relate the direction of the curly E field to changing magnetic fields and fluxes. That's it for this lecture. In our next lecture, we will discuss how the falling magnet and the wire loop with an induced current can exert forces on each other. This will be important for us to understand in order to carry out our upcoming lab.